So, esoteric programming languages. The odd, the fun, and the terrible. Because who doesn't like ripping off old movie titles? So we're going to start with what makes a language esoteric. So in general, an esoteric programming language is not going to be used in common practice due to the fact that it is not made to be practical. They tend to be either, so in general, they tend to fall into either they're made entirely for fun, like Shakespeare, which is a way to more poetically code, and Piet, which the guy made for fun and is kind of interesting. It's entirely done for apps. And then there's also ones that made to prove of concepts such as BrainF, because the latter half of the language contains a swear word, so I probably shouldn't say it. And Piet again, which shows, oh look, you can program with bit apps. Great. All right. So first we're going to talk about Intercal. It is pretty much the original esoteric programming language. Its full name is the Compiler Language with No Pronounceable Acronym. So its acronym is Intercal, despite the fact that it's not an acronym. But so this was created by Don Woods and James Lyon while they were students at Princeton. And Intercal was created to completely flip programming on its head. To take everything that you ever expected that you would have in programming, discard all that, and come up with an entirely new set of operators that were completely roundabout and pointless. Alright, Intercal has two binary operators. I don't mean operates on bits, I mean two operators that take two arguments. So this is where normally things have, plus, minus, subtraction, division. Intercal doesn't have any of those. It has mingle and select. Mingle, which was originally C \/ and was changed to $, because most people couldn't type that on their systems. What it does is it takes two arguments and it interweaves their bits together. So I'll show it later. Select, which is tilde, will select all the bits from the first argument using the bits of the second argument to determine which bits get selected, then right align them in pad and sequence.
Steve, I can probably just hit the arrow key for you whenever you touch your mouse.
Alright, so the mingle, here's an example of the mingle operation. So you have 8 mingle 7, which gives you the answer of 149 again. So 8 is 1000, 7 is 011. So here's 8th bits, here's 7th bits, and then you take 10010101, and that's the end, and that is what you get returned from mingle, which is 149. So that is this will actually kind of almost make sense when we get to the actual unary operators Intercal allows you to use as well, because they are rather limited. So then there's select, which is a more fun beast. So if you take 102, select 90, then you break these also down into the binary representations, and you select from 102 using the bits in 90. So anywhere that 90 has a 1, that bit gets carried down to the final product. Anywhere that 90 has a 0, that bit does not get carried down, and that's what these X's here represent. So then you take these bits 1, 0, 0, 1. You push them all to the right, and then pad the rest of the number out with zeros, so you get 9 out of 102 select 90 in Intercal. So these both seem like extremely strange and pointless operations that you have never seen in any other programming language before, and that was the goal. That was the goal of Intercal, was to be the biggest joke that ever existed. So now Intercal only has 3 unary operators, and, or, and exclusive or. And they don't take, and as they're unary operators, they don't take multiple arguments. So you can't say, I want to bitwise and this variable with this variable. You basically have to mingle them, and then run the unary and operation on them, and then you select defines the appropriate bits to actually get what would normally be a unary and out of it. So the unary operators do pairwise operations of all the bits with a number, and the most significant bit of your result number, which I think is being blocked off by the. That's unfortunate. Oh no, I got cut off. Anyways, but the most significant bit of the result comes from the least significant bit and the most significant bit when you do pairwise operations on that. Actually, didn't make out because the unary operator on the bottom right up. So basically, this is 12. So if you do a unary AND on 12, it ANDs these two to create this, ANDs these two to create this one, ANDs these two to create this one, and then wraps around and ANDs the most significant, least significant bit to create the most significant bit of the result. So AND 12 actually equals 4, and when you do unary ANDs. Alright, there are 4 variable types in Intercal. There's a 16-bit int called a one spot, because they also decided that you shouldn't call anything by its actual normal nomenclature. So period is spot, colon is double spot, comma is tail, and this is called hybrid, because why not? This is not called hash or pound, it's called mesh. And let's see, parentheses are called wax and wane. Quotations are called, single quotes are called sparks, double quotes are called rabbit ears. And yeah, that's Intercal. And their entire instruction manual will only refer to them in that manner. So the 4 variable types are the 16-bit integer, the 32-bit integer called double spot, 16-bit array, and a 32-bit array. And you can also have constants in the and you also have constants usually for assigning, especially for doing weird mingle operations where you want to have, or weird select and mingle operations where you want to know what number you're using to select certain bits. And those are all denoted with a mesh out front. So here's an example line from Intercal code. Please do assign to a double spot integer, or a double spot variable called 1. All the variable names are numbers, and all are assigned using whatever their prefix is from here, and then the number. So this is double spot 1 gets assigned the value of 569, and this operator is called calculate, even though it never really is called that. So each variable has its own stack in Intercal. So all your integers and the arrays have stacks. So you access these with stash and retrieve. So here you have please do, it assigns 3 to 1, stashes the value, so that's now on the stack. Then you do assign 5 to this double spot 1, so the value is now 5. Please don't is how you make a comment, which, well actually in Intercal how you make a comment is you put anything that isn't valid syntax into your program and the compiler ignores it. But if you accidentally put valid syntax, then your comment is going to screw up your program. So normally people instead do please don't or don't, which tells it not to execute that line. The problem is that there are commands that can take, in Intercal, that take please don't or do not, and do what's called reinstating them into the program. So if you have a loop, you could theoretically reinstate this line and have an attempt to run it. It's a bad idea. So now the value is 5, and then it does retrieve, double spot 1, and now the value is 3 after the pop. So stash is push, retrieve is pop, and assign. So this also works with arrays. Fun fact. So you could do the exact same thing if 1 was an array value, and it would store the values of the array in the stack, and then pop them all off and reassign the array. It's pretty great in its own terrible way. Intercal's I/O, it has readout, which will either output in Roman numerals in the original thing. So any number value you have, it output it in Roman numerals, or it uses really weird operations on an ASCII table to generate them in C Intercal. So it doesn't do a straight one-to-one mapping with the ASCII table. Instead, it takes the previous character code that was read in or written out, subtracts the current character code from it, and then does modulo 256 on it to determine what actually gets printed. Lots of fun. The write in Classic was you had to actually write out the numbers. So if you wanted to put 172, you had to write out in English 1 space 7 space 2 in the English words originally. Then they also supported, Sanskrit and Latin and the artificial language Volapük. Because apparently, English is the only actual language that is still used that they supported. And then everything else, they just picked the more esoteric languages to be input to their esoteric language. Are you kidding me? Intercal is great fun. Here's Hello World in Intercal. So, one thing to note, you have the do's versus the please do's. And in Intercal, it is recommended you have 1 please for every 3 non-polite statements that you have, because if you're overly polite, the compiler will reject your code. If you don't have enough pleases, the compiler will reject your code. Also, when you compile your code, you have to make sure to run it with the -B switch, or else it could insert a random error into your code and fail. So, this is really a great language. So if you ever go and look at the error list for it, there's one, I believe, that says if you're using this many quotations, you may as well be plagiarizing. And because quotations are used to determine precedence, and it's like if you have over 60-some quotations nested inside of each other, the compiler just throws that error at you. So they're all really hilarious errors to read through. So essentially, all you really do here is you declare an array of 1 spot type, so 16-bit, so an array with 16-bit integers, you assign all a bunch of numbers to them, and then you do please read out, which you can see Intercal will read out the contents of the array. And if you go and look it up, none of these are the correct ASCII values because of the weird modulo arithmetic it does when calculating each value it's going to print out. And right here you can see an example of a line number. So you can use those as labels throughout your program, because the only looping constructs they really have are these strange go-tos but it's all stack-based go-to, strange, remember where you came from stuff. So it's really fun. And and you shouldn't use line numbers between 1,000 and 100,999 because those are all reserved for system library. You can use anything below it, and theoretically anything above it, though if other people wrote libraries, you have to make sure you don't mesh with those either. So, also there's this great thing which says this line has a 99% chance of executing. This is valid on any line. You can state the % chance that it will execute, and accept any values inclusively between 1 and 99. So you can make a truly random program. And then you always end with please give up, which tells it to terminate. All right, so that was Intercal, a wonderful language. And next we're going to go on to BrainF, which was created by Urban Müller in 1993. This was created in an attempt to have a language with the smallest compiler. I believe that the smallest one is 100 bytes, so yeah, they pretty much hit their mark. It only has 8 operators in the language, and it's one of the many languages called a Turing target, which means while it is Turing complete, and therefore you can do anything a Turing machine can with it, you would not want to. Because to run it takes so long that it's just completely impractical. I think actually on Intercal, they were running a C version of the C of Veracity versus an Intercal one. Intercal took like 17 hours to complete, whereas C took like 7 seconds. So that's how great all these languages are, really. So the operators in BrainF are left caret and right caret, which will decrement and increment the data pointer. So essentially BrainF runs on a giant, you could think of it as a tape, an array, whatever, and you start at point 0, and then these will move you left and right along it, and each one of those contains a value in it, which then you use minus and plus to decrement and increment that value. So essentially you do like right caret plus, and you increment this value to 1, and you can do right caret plus plus, increment that to 2, etc. So period will output the byte at the data pointer, and I believe as a character. whereas comma will accept a byte of input in as a character and convert it to its ASCII value and store it wherever the data pointer is looking. And then the brackets are used for a sort of really primitive looping construct, which is kind of interesting to see. So here's the looping. Essentially, if it hits an open bracket, and it's at a 0, I believe. Yep. So if it hits an open bracket when the data pointer is currently pointing at a 0, it skips down to the matching closed bracket and continues execution of the program. And if it hits a closed bracket while the data pointer is pointing at a non-zero value, it goes back to the matching open bracket and continues from there. So essentially down here, where I could have put this on different lines, but I didn't because, yeah. It increments the first space in the program counter to 3. So the data pointer is now pointing at 3. It goes through, it increments, it goes right one, increments once, goes right again, increments twice, goes back to pointing at this 3 and decrements. So this will loop through 3 times until this first thing is 0, and then skip this and end the program. So if you could actually visualize the array, the first pointer, which is what was used for the looping, is 0. The second pointer, which was single increment, is 3, and then the third one would be 6. So that is loop in this wonderful, wonderful language. And that's my taskbar. So here's Hello World. Great. Essentially, what it does is it sets up this part here in this first loop, increments all these values to multiples of 10, and then after that, it just goes through and like makes the first one 72 and outputs, and then continually goes through and just uses whatever it could find that's closest to the character values that it wanted, increments them, and then outputs a character. Which actually, this was a Hello World that apparently just wanted to not use decrement except in the loop, because you could have done it with a lot less, but fun. So as a final thought on BrainF, the compiler will ignore any non-operands when you go to compile your program. So you can actually put a BrainF program in another functional program, and the compiler will just ignore anything else that isn't a valid character. So if you're careful with your construction, you can embed these in other things. You can embed them in the middle of giant text documents that look like they say something or actually just some giant silly BrainF program. All right, next is Piet, which is really fun to try and understand how it works. So this was programming with bitmaps, and it was made by the same guy who made Chef, which is kind of like Shakespeare in that it makes all your code look like recipes. He made intelligent sort, which was the sort where you pass it a list and it passes it right back to you and says, it must have already been sorted. He made haifu, which is a programming language based on haikus. And he's the one who proposed Bogo Bogo sort, which is worse than Bogo sort. He basically, one of his hobbies is making esoteric programming languages and terrible algorithms, including what he called len encoding for images, where he just went and found the standard benchmark image that people usually do compression tests on, had it so that whenever that image was read, it would just output a 0 to the file and exit. So it only took up 1 bit to encode the entire file, and on anything else, it would just take another encryption algorithm and just prepend a 1 to what that encryption algorithm would put out, and exit. So his argument was this algorithm was able to do 6 million times better than any other compression algorithm for the standard benchmark test, and only did 1 bit worse on any other image, which was trivial. So ergo, his must be the best. But here's Hello World in Piet, and all of the commands in it are based on hue and color in the image and how it changes as the data pointer goes through. So it's an odd beast. I don't know if I'll be able to fully explain it very well, but it's fun. So it's a stack-based language. Everything in it, so whenever you call add, subtract, mod, you don't ever pass them any arguments. It just goes and it looks at the last, for most of them are perform the last 2 elements of the stack. There's a couple that pop like the last 1 and do something with it. Essentially pops them off, performs the operation, and pushes the result back on. And here's a chart that I just fit here because I couldn't lift it anywhere else, which just is supposed to show, so there's 3 different levels of darkness, and these 6 different hues. And if you walk off the edge of this one, it loops back around to here. So, a step from magenta to red to yellow to green is 1, 2, 3 steps. And light is technically darker than magenta, and dark is technically lighter than light if you wrap around. So there's a wraparound on both the lightness scale and the hue scale. And then white and black are just black. Whenever you encounter a black, it will not go there. So there's basically a little pointer that goes around your image, and whenever it hits black, which it assumes all borders to be, it turns clockwise and attempts to go that way. And white, it will slide across and then attempt to turn on white because white provides no other commands. And here are all the commands in the language, which are determined as the data pointer goes across in the image. It will determine which one of these commands gets executed by when it moves from one pixel to the next, by how many shades darker and how many color steps it's been. That's how it determines what to execute. So, here's all of these, which most are fairly intuitive as to what they do. The pointer changes the direction of the directional pointer, and the switch changes another pointer on it. And then the rest of them have input-output. So execution will always start at the top left, pointing right, and as it goes, it'll either go until it hits the border and then turn right again and continue down, or if you put either a command to force it to switch, or you have it run into a black or white block, it will also turn before that. So if the directional pointer cannot find a valid pixel to advance to, so if you put it in the middle of just a giant field of white, it'll go forward and attempt to get off of that white pixel any way it can, and if it can't find a way off, execution ends. So that's how you exit these programs. So here is a BrainF interpreter written in Piet. Yeah, essentially, it has you enter in input separated by pipes, and it can read it all from standard in, and then actually run the program. It's fairly hilarious. And that takes us on to Shakespeare. A really fun thing to do when you're in the middle of engineering fundamentals and computer systems is to play with Shakespeare instead of pay attention. It's a great way to pass the time. So Shakespeare was created by John Ostland and Carl Hasselstone. It attempts to make all of your programs look like Shakespearean plays, and it's really left up to you and your creativity to try and make it look as the least like a program as you possibly can. And it's great fun. So everything in it's done using these positive and negative adjectives versus also positive and negative nouns. And I think I explained that later. And every single variable in it has to be a Shakespearean character. If you don't give it a Shakespearean character, the interpreter rejects it. So the parts of the program. There's the title, which is there, and you never use really. You can type anything you want in there up until the first period of the program. It skips everything. It doesn't care about that. The characters are your variables throughout the program. They all have to be the names of a Shakespearean character, or the compiler rejects it, or the interpreter rejects it. And every single one of them has to have a description, which also does nothing, but they're hilarious to read. The acts and scenes, they don't really do anything, but they act as labels for essentially what they have as go-tos within the language. And then there's enter, exit, insert, which it works by you put characters on the stage, and then they act upon each other, and then you have to have them exit the stage because you can only ever have 2 on at once, or the interpreter blows up. And then your lines are the actual actions that they all do. So to set a variable, you have to have the two actors speak to each other. So if you have Hamlet and Juliet on, which is completely mixing Shakespeare plays here, then you find whether or not the noun on these counts as a positive or a negative noun, and which will add a modifier of either 1 or -1, and then you multiply it by the adjectives in front of it. So if you are a beautiful flighty owl, then whoever was not speaking that was on the stage will have their value set to 4, which is 2 times 2 times 1, because owl is considered actually a neutral value, which is the same as the positive value. Or you could do thou art as kind as the sum of a black cat and a white horse, and by saying, thou art as the sum of something and something else, or the difference of something or something else, or the product of something and something else, is how you apply other arithmetic operators. So so in this case you get 2 times 1 for the black cat, 2 times 1 for the white horse, and then the sum of those is 4 again. The input and output, speak your mind, it prints out the character. Yeah. So whenever you have a character say to another one, speak your mind, the value of the other character that wasn't speaking gets printed. Whenever you say open your heart, it prints, and it'll print the actual numerical value. If you say speak your mind, it prints the character that's associated with that value. Listen to your heart will read in whatever you put in as a number, and open your mind will read in as a character. More stacks. So Shakespeare has stacks on all of these variables, and you say remember to push onto the stack, and recall to pop off the stack and then assign it to whoever you're talking to. So if Hamlet says thou art as dumb as a boiled cabbage, it sets whoever he's talking to 2. If he says remember thyself, and then pushes their value onto them. So now on their stack they have 2 as their value. Hamlet now says this line, which I'm not reading, and that assigns them a value of 8. He says recall your transgressions, pops off the 2, reassigns it to them, and then if he says open your heart, it would print 2. That is fun in Shakespeare. So here is the top of the Hello World program in Shakespeare, because it is god-awfully long. I think, yeah, you put an H and an E here. That's as far as you get. But up here is the title with the period, which apparently meandered down to the next line. Here's your characters section, where you say Romeo, Juliet, and Ophelia, which is the important part, and you can write whatever you want over here. Then Act 1 and Scene 1 are defined here. And in more complex programs that aren't Hello World, like you would actually have down here, if you wanted to go back to those, you would say let us go to Scene 1, and it would jump back to Scene 1 and re-execute. And here Hamlet just insults Romeo. So Romeo has his value set to this, and then to this, and then speak your mind is called, and it'll print a capital H, and then he sets into some other value, which is the ASCII code for E, says speak your mind here, prints out an E. It's a really fun language to mess with, and it's a good way to get through engineering fundamentals of computer systems. Yes, Elliot?
Is iambic pentameter enforced by the compiler?
It's not enforced. It's encouraged. Just like as I didn't do on the slides for space constraints, but just as tasteful tabbing and spacing are also not enforced, but greatly looked up upon. You should read their documentation. All the documentation for these are great, except for Malbolge. Yes?
So are there neutral adjectives?
So the adjectives, their positivity, negativity, I don't believe actually affects the final value. Everything just multiplies by 2. If it's an adjective, it's the nouns that they reference that. If it's a positive one, it's the positive one. So it's a positive noun, and that's a positive 1. So any adjective you stack in front are 2 times 2 times a positive 1. When it's a neutral one, it's still a positive 1. I don't know why they really made the difference. I guess just in taste of, well, this isn't really a positive adjective, but we can't really do anything other than positive or negative one, so it's just a positive one. Then negative adjectives, I believe codpiece is one of them. That constantly reappears in their example, probably reappears on this example back here.
Yep.
Yep, is a negative one. And so when you multiply 2 times 2 times negative 1, it'll give you a negative value.
You can actually use
Oh, but
Shakespeare.
for the record about the neutral, it's just so you can have something that doesn't exist. Because the neutral world list doesn't exist.
Great. I didn't go through and look at the word lists.
So there's only positive and negative.
Alright, here's Malbolge. A wonderful language that no one should ever write in because it's impossible. So this was written by Brian Olmsted, and it's named after the 8th circle of hell, because that is what it is to program in this language. So it was supposed to be impossible to write useful programs in, and someone actually went through, analyzed the algorithm, especially because it does encryption in the middle of its determination of where to move the program pointer, or the program pointer next. So someone did cryptanalysis on that to try and break it so they could actually like write something, and it was bad. But it was 2 years for any program to show up that was written in it, and that was written by a computer doing some insane search on it, justifying a program that could be run and not fail. And it took 7 years for the 99 bottles of beer on the wall that, you know, normally is one of the first things that people write in the language. It took 7 years for anyone to be able to write that in this language, because that is how ridiculously difficult it is. So Malbolge has 3 registers. It has the A register, which can hold an integer value. It has the C register, which is an instruction pointer. It has a D register, which is a memory pointer. And when you start this, whenever you load a program in, it loads it into the start of the memory. Then all the rest of the memory, it says later in the slides, but all the rest of the memory is just filled up with garbage. And so the memory pointer has to wonder over that, and hopefully not do something stupid. Registers D and C can be dereferenced. So A can only hold an integer value, you can't dereference A. But C and D are constantly dereferenced by these programs to do really stupid stuff. And everything under the hood is not represented in binary, it's represented in ternary. So there's lots of strange, so 0, 1, and 2 are the values that all the numbers will be converted into to do really weird, stupid math on it. Like, crazy operations later. But Malbolge has only 8 instructions, just like BrainF and a couple other languages. There's the jump instruction, which says dereference your memory pointer, add 1 to it, and jump to that space in memory. There's out A, which just prints what's in A, and in A, which just stores what's in A, or stores input to A. There's actually, there's not crazy dereferencing stuff going on. There are actually 2 very nice operators. There's rotate and move, which rotates the value at the dereference. So you dereference D, rotate it in a ternary fashion. So it converts it converts decimal or binary, whichever way you want to envision it in your head, to ternary. So 0, 1, and 2. Rotates the digits left. So the leftmost digit goes to the right and everything else shifts over. Then stores the result both back in D and then also copies it into A. Move D to D. Copies the value of the dereference of D to D. So you copy the value that the pointer was pointing to the pointer. CRZ stands for crazy. That's a great operation. Which performs a crazy operation on the dereference of D using the value of A as the second input, because it's a 2-input operation that just basically does substitution across this strange ternary thing that you can go look it up on the internet. It's really weird. To produce a completely different value and then copies that into A. NOP does nothing. That's a great instruction. Useless as shit. And it just terminates the program. So the even more fun part about all these is that each one of these numbers has a numeric identifier, a single numeric identifier between the values of like 0 to 94. Yes?
So what's the point of rotate?
Oh, so here's the thing. You can't do addition or subtraction, or multiplication, or anything else. You have to do everything by rotating the numbers around, copying them, and doing stupid crap like that. That's the point of rotate.
Okay.
So all these instructions have a numeric identifier, and when the program pointer gets to it, which is C, it determines what it's actually going to execute by taking what's at that reference, adding the value of the pointer itself to it, and then doing modulus 94. And that is the instruction that gets executed. And then after this, it takes what actually gets executed, so it takes the result of this equation, encrypts it using a substitution cipher, and puts it back there. And then it increments the program counter and the data pointer. It doesn't, leave the data pointer alone and continue with the program counter. No, it increments what you're pointing at. And there's a crazy operator, which just performs substitution using 2 inputs in a table. So, just as an example, because I didn't want to print the chart up here, the crazy operation of this number and this number creates this number, which there is no rhyme or reason to why it does it. It just does so across a substitution table and prints this out here. Here's Hello World. It's great. This is why nothing got written for 2 years. I believe the first program to be written was Hello World. It wasn't this Hello World though, because the Hello World that got written was done incorrectly. They didn't capitalize the H. One point exclamation point at the end. The guy just said this is good enough and said, "Look, I made something in this language." So when you initially load the program, it loads this into the first, all the memory this takes up. And then all the rest of the memory cells, it just applies the crazy operation. So initially it applied on these last 2 to fill the next cell, and these 2 to fill the next cell, and it just continuously applies that all the way down until it hits the end of memory that the machine takes up. So you just have a bunch of garbage sitting around in the remainder of your memory, which if you look at what all the operations can do, you could very easily just find yourself sitting in the middle of that, despite the fact that you did not make it. Which is why it takes so long to do anything, because these all have to be carefully crafted, so that when the operations are performed, it ends up in here somewhere, or and this is actually predictable as to what it'll do, but you hope to end up in here somewhere, and not off in all the land of the rest of the garbage. So in conclusion, esoteric programming languages are mega fun. Never use them for anything that isn't just experimental fun, because they're slow, they're terrible to write, they don't like to provide operators that are useful, but at the same time you can then post your Malbolge programs to the internet for bragging rights, sit around throwing Intercal programs at people and saying guess what this does? And they won't know. And here's an owl. Questions?
Are you fluent in any of these?
Fluent? Well, I can do Shakespeare, but that's Shakespeare is the easiest out of all these. You just write some adjectives and a noun and just sit there beforehand and scribble out, that's 2 times 2 times 2 times 2, which is this number, and then do this.
If you don't want people to understand the code you wrote, couldn't you just use Perl?
Oh.
Oh, holy war in the lab.
I think Malbolge speaks Perl.
Malbolge does beat Perl. It looks like Perl,
No, because
but
the garbage it fills the rest of your memory with is still well defined, and you could use that in your program if you wanted to.
Pollock.
I'm wondering if you remember the name of this language. I don't. I've not been able to find it, but I just was searching a couple minutes ago. There's another esoteric language which I think almost would probably be harder. It I think has 9 instructions possible, and they're arranged in a 3x3 grid. And then it hashes your current code and then it redefines that table based on it. So every character in your code has a completely different instruction set because it takes those 9 instruction sets and rehashes your entire code from before it into those characters.
That's great.
So
I don't know what it
redefines your
is,
instructions.
but it's great. These are all great languages for the fact that they're terrible. All right, any other questions? All right. Here's an L.